So, good morning, everybody. Welcome to this session on graphs and networks, where the networks are. We have 6 papers today, and as usual, there's the possibility to ask your questions over the Slido channel. And I would say let's start right away with the first talk, which is given by Mengjie Wang, Visual Analysis of Multi-Outcome Causal Graphs. We cannot hear you.
Oh, yeah.
Yeah.
Can you see the slides?
Yes, please go to the first and start. Yes, good.
Okay. Hello, my name is Mengjie, and welcome to our talk on visual analysis of multi-outcome causal graphs. This is a joint work by authors from different institutions. Understanding causality is fundamental in many domains. Causal discovery is to learn graphical structures with a causal interpretation. In medicine, experts seek to discover causalities between potential risk factors and a specific disease. They would also like to understand the similarities and differences between different yet related causal relationships among different diseases or outcome variables to assist in intervention and treatment. For example, different factors may influence the development of diabetes and hypertension, but they may also share some factors. Many previous work have explored the visual causal analysis. For example, engage human experts, utilize uncertainty-aware causal graph, recover causalities in event sequence data. Other works focus on visual comparison of causal graphs. For example, apply superposition for graph comparison and compare graphs from multiple algorithms. Prior methods on visual causal analysis and causal graphs comparison mainly focus on single outcome or pairwise comparisons, but lack support from multi-outcome causal graph analysis using state-of-the-art causal discovery methods. To address the aforementioned unsolved problem, we had a long-term collaboration with 3 clinical medicine and public health experts following the design study methodology. Our major contributions are as follows: a 2-stage visual analysis for multi-outcome causal graphs, progressive visualization, and interactive controls of multiple causal discovery techniques, including modern continuous causal discovery methods, graph layout and visual designs that support effective comparison of multiple decks, a case study and expert user evaluation using real-world health research datasets with medical experts. We abstract the domain problem into 2 data analysis stages as shown in the figure that explains our workflow. Combining feedback from domain experts with design principles from previous causal analysis related visualization works, we further specify the following 6 design requirements. Based on these requirements, we firstly come to the first stage of single causal graph analysis. None of algorithms can yield good results for all datasets. Here is the visualization of the true causal graphs, the left column, and results of the 3 causal discovery algorithms, the right column. Classic PC algorithm is in black. DEC-GN with continuous optimization is in blue, and HCM specialized for mixed type data is in orange. We yield higher accuracy with the combination of 3 methods, and the increased false positive rate can be mitigated by the expertise of domain users rather easily. The combination of these algorithms provides users with important additional information for creating a better causal graph than using any of them alone. We apply different visual channels to encode different characteristics. Our comparative visualization uses the superposition of results from PC, DEC-GN, and HCM with different edge colors encoding. Node color or shape encodes common or outcome variables. Edges encode causal relationship. The direction is by default from the upper node to the lower node. Thickness encodes causal effect magnitude, and solid lines for positive and dashed lines for negative effect values, respectively. We progressively draw intermediate results at each epoch by updating the graph edges within the current layout. The line chart shows the measurements of depth GN at each epoch. To gain more insights into the variables of the causal graph, a multidimensional visualization is available in our method to show the distributions of variables of mixed types. Here is the user interface of our visual analysis system for single outcome graphs, which consists of 3 views: dataset and variable selection view, allowing for dataset and variable selection; single directed graph view, allowing for graph editing; and the variables matrix view, providing insight for graph editing. Then we come to the second stage of multi-outcome causal graph analysis. We combine all single graphs of interest as one large causal graph, namely the supergraph. The supergraph is laid out using the aforementioned layered method and can show the similarities and differences between the subgraphs. Because of the global image space and anchored common nodes, the supergraph properly supports comparing up to 2 or 3 outcomes, but does not scale well for more outcomes perceptually. We can directly extract subgraphs from supergraph. However, it uses large empty space. So we create a comparable graph layout to facilitate the comparison of more than 2 subgraphs extracted from the supergraph. We formulate an optimization problem to preserve the relative position of the nodes and compress the empty space. Please refer to our paper and supplemental material for our method to approximate this optimization problem. As shown here, our method uses smaller horizontal stress numbers compared to directly extracted subgraphs. This suggests that our layout leads to edge distances closer to the graph's theoretical distances than directly extracted graphs. In addition to layout optimization, we also design visual mappings to facilitate comparison. The visual encoding on edges is the same as for single causal graph. Rather than all 3 causal discovery results, only the final user-edited causal graph is shown. Note color here encodes different outcome graphs. Reference grids can aid the comparison of the global position of nodes. Arrow glyphs can encode the extent and directions of compression. A thumbnail is provided at the bottom left of each subgraph to further indicate the global position of the subgraph. In the second stage, users can select graphs of interested outcomes and compare them using the supergraph or subgraphs with the new comparable graph layout to identify shared and distinct influencing factors. Please refer to our supplemental video for the analysis process. To demonstrate the usability of our multi-outcome analysis system, we applied our approach to 2 health research datasets, CHARLES and UKB. We invited 1 domain expert to participate in our case study, which consists of 3 parts: demonstration, expert explorer, and post-study interview. Here is the case study of UKB data with a medical expert. Single causal graph analysis is demonstrated in views 1 to 4, and multi-outcome causal graph comparison is demonstrated in views 5 and 6. Here are the comments and feedback of our case study. For example, each algorithm is partially consistent with domain knowledge. Insights gained are in line with the expectations of the expert. Similar results exist in the CHARLES dataset. We also invited 3 domain experts to evaluate our system using sync-allowed protocol. All experts rated the 2-stage analysis frameworks positively, and they provided further comments regarding our visual analysis tool as listed below. Feedback suggests our visualization and visual analysis tool is useful for the address of the aforementioned domain problem of multi-outcome causal graph analysis. In conclusion, we propose a two-stage visual analysis for multi-outcome causal graphs with various visualizations and evaluate the usability of the tool with domain experts. The code for this project is open source available. And we would also like to improve our method by improving variable selection techniques, supporting the analysis of causal graphs with external evidence, expanding to temporal datasets for time-dependent causal analysis. Our work is supported by these findings. That's all for my presentation. Thank you for your attention and any questions.
Thank you very much. Very interesting. Since there are not yet questions, I see, I might start with the first question. Maybe a very silly question from a non-expert. Where do these differences of the causal discovery methods come from? Why are they so diverging?
I think it's not just for the medical area. It's diverging for all areas, in fact. The causal discovery method yeah,
here we see the differences.
Yeah, there are many different causal discovery algorithms in this area itself. It's not just for the medical medical area. The causal discovery typically there are typically 4 categories for the causal discovery algorithm. For example, constraint-based, score-based, structural, asymmetric-based, and those exploring various forms of intervention. Here we chose 3 different algorithms. The PC is the backbone approach, which is a very classical discovery method. And the DAC-GN is a more recent one that represents the continuous optimization. And the third one that
you just took them, and I mean, it's just an input for your method. You just selected them, right?
Yeah.
Good. I have a question from the internet. From a design perspective, having too many edges can lead to visual clutter, making the interpretation difficult. How can this issue be solved? It's like when things are getting more complex, when you have many of these edges, what do you do then? Do you have some kind of simplification?
You mean the evaluation?
No, in the resulting graphs, I guess the person asks, if you have too many edges, can you deal with that and maybe simplify the results?
Yeah, yeah. We in the first stage, in fact, there's a video, but I don't provide the complete video. In fact, in the first stage of the single causal graph analysis, the domain expert can use our visualization to edit the graph. For example, add or delete an edge, or reverse an edge, and also can add or delete node.
Okay. Good. Thank you again. More questions you can directly answer in the Slido. We move on to the second paper, which is structure-aware simplification of hypergraph visualizations, and the presenter is Peter Oliver.
All right. Hello. Can you all see me?
Yeah.
Okay. All right. Okay, hello, my name is Peter Oliver. I'm a PhD candidate at Oregon State University, and I'll be presenting our work on structure-aware simplification for hypergraph visualization, which is a collaboration between myself and my advisors, Dr. Eugene Zhang and Dr. Yue Zhang. Hypergraphs give us an effective way to represent networks of polyadic relationships over sets of entities, which we can visualize in 2D with touching polygons in what's known as the polygon visualization metaphor. In this metaphor, entities are represented as dots in the plane, and polyadic relationships as polygons whose vertices align with the positions of the entities. In the language of hypergraphs, each entity is called a vertex, and each polygon or polyadic relationship a hyperedge. In this paper, we focus on larger structures that arise among subsets of the vertices and hyperedges, such as this cycle structure here. We propose a topology-inspired decomposition that breaks down an input hypergraph according to its constituent structures, including topological blocks, where all of these cycles in the hypergraph live, bridges, which are tree structures that connect multiple topological blocks together, and branches, which are also tree structures, but only attached to a single topological block. We believe there are many possible uses for our decomposition, but in this paper, we use it to guide a structure-aware simplification method that preserves significant structures while reducing visual clutter in polygon visualizations. To help illustrate why we believe that structure preservation is important, let's consider a dataset that represents friendship relationships between students in a high school setting. Here, the cycles can tell us something about how close-knit different connected subsets of students are. For example, in this outlined area contains numerous small cycles and could represent a close-knit community like a class or school club. But there's actually a longer cycle hidden among the overlapping hyperedges that indicates some separation within this community. And to make these kinds of features more readable, we might turn to a simplification scheme, such as the one from Oliver et al. 2023, whose priority-guided simplification scheme is based on local per-element statistics that affect the complexity of layout optimization algorithms. However, they do not take into account larger hypergraph structures. Applying their simplification method to our friendship dataset, the highlighted cycle is completely collapsed, and the adjacent friendship communities are misleadingly merged around a single vertex. This presents some challenges, as the loss of meaningful structures can make simplified visualizations less reliable, and this is the main issue that we aim to address in our paper, but there's also this related question about visual clutter and whether the overlapping polygons are in fact unavoidable or if they're just the result of a suboptimal layout. To address these challenges, our proposed method first decomposes the hypergraph into its constituent topological blocks, bridges, and branches, and we further analyze the cycles within the topological blocks to pinpoint where the unavoidable polygon overlaps occur. Finally, we simplify each structure according to its type using a custom set of simplification operations. Now, looking at the result of applying our structure-aware simplification to the friendship dataset, we see that the highlighted cycle is preserved and the adjacent friendship communities remain separate. We don't have time to go into all of the details, but our decomposition is based on the bipartite graph representation of a hypergraph, where the hyperedges and vertices are all replaced by graph nodes. Edges in the bipartite representation indicate containment of a hypergraph vertex in a given hyperedge. This also leads to the concept of the dual hypergraph, in which the roles of the vertices and hyperedges are reversed. For clarity, we often refer to the input hypergraph as the primal hypergraph. The primal and dual hypergraphs have the exact same bipartite representation, so by defining our structures based on the bipartite graph, we have a one-to-one correspondence between the structures in each representation, and we're not showing any bias toward the primal or the dual. A cycle in the bipartite graph corresponds to exactly one cycle in the primal and dual hypergraphs among the matching hypergraph elements. The same is true for our topological blocks, which are maximal biconnected components in the bipartite graph, and our bridge and branch structures, which are the leftover tree structures. Of course, this means that our bridge and branch structures are planar by nature, so we know that any unavoidable polygon overlaps must occur within the topological blocks. This led us to investigate the cycles within the topological blocks, and by looking at a basis for the cycle space, we found that the so-called forbidden subhypergraphs introduced by Oliver et al. 2023 occur among groupings of minimal cycles in the bipartite graph, by which we mean the smallest possible cycles in a bipartite graph that happen to have length 4. This brings us to our structure-guided simplification method, which operates directly on the bipartite representation and incorporates a minimum cycle collapse operation used to eliminate unavoidable overlaps caused by forbidden subhypergraphs. And our cycle edge cut operation, on the other hand, is used to eliminate any non-planar configurations among the longer cycles in the topological blocks that might arise because of the Kuratowski subgraphs. These first two operations are only applied within the topological blocks, and our final leaf node pruning operation is only applied to bridge and branch structures, with the aim to reduce the amount of space that they require in polygon visualizations. Now, the names of our operations are fairly self-explanatory. A minimum cycle collapse merges opposite corners of a length 4 cycle together, thereby collapsing the cycle. A cycle edge cut removes a single edge from some long non-minimal cycle inside a topological block. And a leaf node pruning operation deletes a leaf node from a bridge or branch structure. Now, putting this all together, we first decompose the input hypergraph, separating the topological blocks from the bridges and branches. Then we analyze the cycles within the topological blocks, identifying unavoidable polygon overlaps by looking for groupings of minimal cycles. And we also extract long cycles with the goal of preserving them during simplification. We then apply our minimal cycle collapses, any cycle cut operations, and thin out the bridges and branches with leaf pruning operations. We then re-optimize the layout of the simplified hypergraph, and we can observe that all but the cut long cycle are preserved in our simplified result. Turning now to some additional results. Here we have a paper author dataset where each vertex represents a researcher and each hyperedge represents a published paper. In this case, we only applied minimum cycle collapse and leaf node pruning operations, but not any cycle edge cuts. So there's still some entanglement among the long cycles present in this dataset in our simplified visualization. One thing in particular that we notice comparing our results with those of Oliver et al. 2023 is that this branching structure in the upper left actually contains a cycle toward the end, which is preserved in our simplified result, but simplified away in the previous approach. Similar to what we saw with the friendship dataset, the previous approach collapses multiple structures around a single high-degree vertex, which in this case gives the most misleading impression of a single, very prolific author. And our new approach, on the other hand, maintains the cycle and these small branch structures and the bridge structure within this circled subset of the hypergraph. And it gives a more accurate impression of the size and collaborations within this particular subset of this research community. We also apply our method to a dataset representing face-to-face interactions between visitors to a museum gallery. In this case, we primarily applied cycle edge cut operations to disentangle the long cycles that are present in this dataset. And we've added some additional dotted line annotations to indicate the connections that were cut during the simplification process. On the right of each subfigure, we highlight two disjoint paths in blue and orange from the top to the bottom of the visualizations, which in this context could represent multiple possible transmission vectors for an infectious disease. In the input hypergraph layout, these paths are crossing multiple times and perhaps difficult to distinguish because of the entangled hyperedges. But in our simplified layout, we can more clearly see that they are, in fact, disjoint except at their endpoints. To conclude, we make a number of contributions to the theoretical side of hypergraph decomposition and simplification. Our goal with this work was really to lay the groundwork for future hypergraph algorithms that are structure aware. And we have a number of ideas for future work in this area, including a hierarchical layout method that leverages these extracted hypergraph structures and uses them during layout optimization. While it's not part of our immediate planned future work, I also want to especially highlight the need for additional evaluations through user studies and comparisons to fully explore the potential benefits and drawbacks of our technique across a range of different applications. I want to thank you all for listening, and I would be happy to take any questions.
Thank you very much. Fascinating topic. So are there any questions? I'm checking up the web. No, not yet. Maybe one question from my side. Why don't you combine your simplification with a little bit of relayouting? So I have the feeling that you can do even the results can be even better visible if you just slightly change the results. Is that a completely different thing, or have you thought about that?
So you're talking about
So in your
performing-
simplified graphs, you still have like places that are not very much simplified due to the structure of the input. So can you do something with like trying to relayouting them a bit to get like better structures?
So yeah, in our previous publication, we presented a layout method that used these simplified hypergraphs and through an iterative process first simplified the hypergraph and then reverse simplification while adjusting the layout to get to a better layout for the input hypergraph. So we've looked into that a little bit. But yeah, I think coordinating the layout with the simplification has been a focus for us, and hopefully we'll be able to look more into it in the future.
Yeah. So I see no more questions. Then thank you again. And we move on to the third presentation. Does this have a particular meaning? Interactive pattern explanation for network visualizations by Xinhuan. We cannot hear you yet. No.
Yeah, sure. Okay, thank you for the introduction. And hello, everyone. I'm Xinhuan Shu from Newcastle University. And this paper is in collaboration with Alexis, Pister, Junxiu, Tang, Shen, Chevalier, and Benjamin Bach. So today I will present this work about a new interactive technique to explain visual patterns and support visualization learning. So how does an analyst usually learn an unfamiliar visualization? If we take the adjacency matrix as an example, usually they should know the visual grammar of this matrix, like the meaning of each visual mark and the graphical encoding and the spatial configuration. And they may find these instructions from like visualization books, courses, websites, and also there are lots of online tutorials. Well, we agree that these materials provide general knowledge about visualization. A recent learning material called Visualization Cheat Sheet has looked more deeply into how to interpret visual patterns embodied by the visualization. But although we have all these resources, we observed that the analysts may still face the challenges in this process, especially when the visualization applies to the real data set. So in our preliminary study, after learning the visual encodings, we found our participants still have some questions and ask us, like, this area looks like a bug. Does it have a particular meaning? So such kind of bug is not the only confusing example. Analysts point out other examples, like here, the fish-like area, the crosses, and so on. So we see these should all be visual patterns, but may not look as the same as those in the instructions. So the analysts who are novice in visualization often get confused and usually misinterpret them. However, being able to quickly spot and interpret these visual patterns is essential to using a visualization as defined in the visualization literacy. So which requires the ability to confidently interpret the visual patterns in the visual domain as properties in the data domain. We found there are similar descriptions in all of like literacy definition. Then the problem is, how can we support people to quickly interpret visual patterns? Here are our solutions. We propose interactive pattern explanations to support visualization learning, which explains the visual patterns and their corresponding data patterns on demand, and also in a user-defined part of the visualization. And we take the network visualization as our starting point in this paper. Here, I'll still use the bug example for demonstrating how our tool works. So when the analyst spots this bug, they don't know how to interpret that and want to see whether this is a meaningful pattern. So the user could select this area, and our tool will automatically look for all possible network patterns in the selected node and links. So using our pattern repository that is inherent in the tool. And this repository contains 11 network patterns and 34 visual patterns across 3 network visualizations. So with the mined results, a selector pop-up then shows with a list of network patterns. For example, this case here, you can see we show your selection has 4 network patterns, including true clicks and true strong links. But if the tool doesn't find any specific patterns, it will just pop up a brief message like that your selected area doesn't correspond to any specific network patterns. So here in this case, if you don't know what the click pattern is, and you could click it on the top menu, and the pop-up then updates to show the explanations of this chosen network pattern, as well as the corresponding visual pattern. We will use both visual and textual descriptions in the explanation, similar to the cheat sheets. And moreover, the tool allows the user to browse other instances of the same network patterns in the visualization. The user can hover it, and the tool will highlight the corresponding areas in the visualization. So now you know how our tool works, but how can we develop this system? It might be more difficult than you think. So the core of this tool is establish a mapping between visual patterns and network patterns. But none of these parts are clear to us. First of all, we are surprised that the community lacks a formal and generic definition of visual patterns. Related literature used to describe the visual patterns in the context, such as chains, outliers, or a meaningful whole, but without a clear definition. And to make the meaning of these visual patterns, we need to formalize network patterns that can be explained. And finally, the mapping is vague. There is not always ideal one-to-one mapping between the visual patterns and the network patterns. So to investigate these challenges, we conducted a scoping study and chose 3 network visualizations to start with. And we provided the textual explanations of these visual encodings to the participants and asked them to tell us what visual patterns they've seen in the network visualization and which confused them, and they required more explanations of that. And here I showcased some patterns participants circled in this visualization. And this also contributes to the pattern repository in our tool. So based on this study, we propose a working definition for visual patterns. And they are visually salient structures in a visualization that somehow catch an analyst's attention. And this definition describes visual patterns from both design and human perspectives. And for simplicity, we describe a network pattern as a topological structure in a data set with some meaning. And in this paper, we focus on network motifs. Finally, the most tricky part is the mapping. And we summarize 5 different possibilities for such mapping. For the time being, I just skip this, but you can find more explanations in our paper. And our tool covers all of these above situations. So this contributes to the foundation of our tool. And the final question is, does this interactive pattern explanation really help learn visualization? So we conducted 2 complementary user studies for evaluation that collects both qualitative and quantitative data. And we compared our approach with other true learning interventions, text-only explanations, and static cheat sheets. So the result confirmed our assumption, showing that participants trained with interactive pattern explanations can correctly find more patterns. So you can see the number was significantly increased compared to the static cheat sheet. And in addition, participants with pattern explanations pointed out more patterns in total and showed a slightly higher accuracy means compared to the cheat sheet group. And if we check the number of individual patterns, we found that pattern explanations are useful for learning complex patterns. And other qualitative feedback suggests that participants appreciate the interactive pattern explanations being intuitive and integrated with visualization. So they could provide in situ and on-the-fly explanations and also validate their understandings. But in contrast, cheat sheets were perceived as a more comprehensive list of patterns to look up. And there are also potential issues and good suggestions. For example, several participants mentioned that they trust the explanations very much, and they were afraid that they could not recall important information without the tool. And another issue is the inconclusive hit and miss. So where participants expected to have explanations, but our tool detected nothing. And they also expected more guided, progressive, and personalized tutorials in the future. Finally, through this work, we call for a more comprehensive critical theory of patterns in visualization. And given the importance of visual patterns for visualization, as well as the fuzziness and the variations, we really need a theory that could facilitate to describe, analyze, and evaluate visual patterns in visualization. And this theory could become a structured way to scrutinize the visualization design. Meanwhile, we should keep the risk in mind, avoiding develop narrow mind and over-reliance on interactive pattern explanations. So the visual patterns should be considered as a thinking tool for reasoning about data instead of a dogmatic way. We should also devise valid ways to evaluate the success of any learning interventions. And that's all about my talk. Thanks for listening, and feel free to ask any questions.
Thank you very much. We have two questions in the internet. The first one is, how was the repository of your patterns created?
Yeah, so basically we do the scoping study. Oh, sorry, not this one. Like here, we collected some like patterns circled like annotated by our participants in the scoping study, and we also circled some of them by ourselves based on some literatures. Mm-hmm. And we that's all.
But there's no like standard kind of set. You collected them based on your experiences and based on previous publications.
Yes. That's also we think is like very important for the community. Maybe we should all like make some efforts to collect this kind of visual patterns.
Yeah. The second question is, these patterns are given as explanations for the visual patterns, but do the participants fully understand the network patterns?
Yes. I think most of them are, most of these network patterns are like easy to understand for our participants because we provide some like textual and visual descriptions together. So they are seeing that they could understand them from these descriptions. But we also do some like simplifications here. We remove some like true complex patterns. Yeah.
Okay, good. So the rest, please answer the more questions directly. Thanks again for your presentation. And
Thank you.
Move on to the fourth paper, SmartGD, a GAN-based drawing framework for diverse aesthetic goals. And it's given by Xiaoqi Wang.
Thanks for the introduction. I will go ahead to share my screen. Hi everyone, I'm Xiaoqi Wang from the Ohio State University. I'm here to present our paper called SmartGD, which is our collaborated effort with Yahoo Research. The main objective of this work is to develop a novel deep learning-based graph drawing method that is general enough to optimize any quantitative aesthetic. To be specific, take a graph adjacency matrix as input. SmartGD will output a 2D graph layout that complies with any predefined quantitative aesthetics. Those are some popular quantitative aesthetics. Traditional graph drawing methods are often developed to optimize one specific aesthetic. However, if people want to draw the graph with minimum edge crossing, it is not an easy task.
because they might feel difficult to choose or even find a desired method without sufficient background knowledge in graph drawing. Recently, several methods have been introduced to flexibly optimize any differentiable aesthetic. For example, GD square is a gradient-based method that optimizes one graph layout at a time. DeepGD is a deep learning-based method that directly uses the differentiable aesthetic as the loss function. As you can tell, they all rely on the differentiability of aesthetic to perform the optimization over graph layouts. However, developing one method to optimize any non-differentiable aesthetic are much more challenging because their gradient does not naturally exist. One potential solution is to manually design a differentiable surrogate function for each non-differentiable aesthetic, such that the existing gradient-based method can be applicable to optimize over this surrogate function. But such workaround is time-consuming and lack of adaptability to any non-differentiable aesthetic. In this work, we develop a GAN-based graph drawing framework called SmartGD that could optimize any quantitative aesthetic, including both the differentiable ones and the non-differentiable ones. It is a general graph drawing framework that does not require additional effort to optimize any aesthetic as long as the aesthetic can be mathematically defined. In order to develop a method to optimize any quantitative aesthetic, we need to train a model that indirectly learns how to optimize the metric function without the needs of computing its gradient. One naive approach is to learn a differentiable surrogate function that predicts the value of original aesthetic metric. However, this is not practical because aesthetic function can be very hard to learn, which might require a very large neural network and a huge amount of training data. Instead, what if we just train a discriminative model that can tell what is good and what is bad in terms of that aesthetic metric? This information alone is good enough to allow us to optimize the aesthetic metric indirectly without knowing the exact value of that metric. The benefit is that a discriminative model is much easier to train than a surrogate function, since it simplifies the problem into determining the relative goodness of a pair of layouts based upon the target aesthetic. It is interesting to see that the discriminative model here is exactly the discriminator from relativistic GAN. Therefore, we design our method with RGAN as a fundamental building block. Our model is consistent of a generator and a discriminator, which are both graph neural network-based model. First, the generator takes a graph adjacency metric as input and produces a fake layout. Then, the discriminator predicts the relative goodness between the real layout and the fake layout in terms of the aesthetic metric, where the real layout can be generated by any existing graph drawing method. Generally speaking, the generator's goal is to generate a fake layout with a higher quality than the real layout, whereas the discriminator's goal is to correctly identify which layout has a better quality. In theory, the fake layout generated by the generator can hardly outperform the real layout. This fundamental problem will become even more severe in graph drawing because we cannot obtain a globally optimal layout as our real example. In other words, simply adopting RGAN will constrain the quality of our generated fake layouts. Then we can never generate the optimal layout with respect to the target aesthetic. To solve this problem, we introduce a self-challenging mechanism on top of RGAN. In this mechanism, an evaluator will evaluate the aesthetic of both real and fake layout. Then select a winner layout based upon their aesthetic value. After each training epoch, the winner layout will replace the current real layout for future training. As a result, the real layout will be improved continuously with respect to the static metric during the training of SmartGD. Thus, it allows SmartGD to constantly learn from better and better examples over time. In the end, the quality of our generated layout will never be constrained into suboptimal state anymore. Here is the end-to-end architecture of SmartGD. Both the generator and the discriminator are composed of a sequence of graph neural network layers. The generator takes a adjacency matrix as input and generates a 2D graph layout. The discriminator produces a goodness score for input layout, which could be either fake or real. To stabilize the input layout distribution, we specifically design a stack of canonicalization layer in the discriminator. This canonicalization layer significantly improves the discriminator's generalizability and speed up the conversions. To demonstrate our effectiveness, we have conducted extensive experiments on optimizing different aesthetics and compare with 10 existing methods. This existing method include force-directed method, gradient-based method, deep learning-based method. Here is the quantitative evaluation for SmartGD. In this table, each column here represents a specific aesthetic metric, each row corresponding to one method. The top part is our method on optimizing different aesthetic. The best metric per column is in Bach. As highlighted in red boxes, our model outperforms the existing method on most of popular aesthetic metrics by a large margin. In terms of the qualitative comparison, here we present 3 different drawings by a different method for the same graph. The layout on the left is generated by Nito, which is a traditional method that optimizes stress. We can see that there are 2 crossings in the layout. The layout in the middle is generated by SmartGD with minimizing number of crossings as the aesthetic goal. We can see that there's no crossing at all, which is exactly what to be expected. The layout on the right is also produced by SmartGD, but the aesthetic goal is to minimize the stress while maximize the crossing angle. We can see that it generates a very similar layout compared to Nito, but there's only one crossing in the layout, and the crossing angle here is almost 90 degrees. That match perfectly to the desired property specified the aesthetic goal. SmartGD also works well on large graph, which showcases the generalizability of our method. In conclusion, this work moves one step further towards a general graph drawing solution for optimizing any quantitative aesthetic regardless of their differentiability. We propose a novel GAN-based graph drawing method to optimize diverse aesthetic goal. We introduce a self-challenging mechanism for GAN to allow us to indirectly optimize non-differentiable aesthetic. Our experiment showcased the effectiveness and the generalizability of SmartGD. Please check our paper and code for more details. Thanks for listening. I'm glad to take any question you may have.
Thank you very much for this interesting talk. We have a question. If I want to optimize multiple aesthetics, does that require to train separate SmartGD models to do that?
Very good question. So it actually depends whether you want to optimize multiple aesthetics simultaneously or separately. So because our method actually can optimize any quantitative aesthetic, meaning that you can just have a weighted average of multiple aesthetic and optimize all of them at the same time using one model. But if you want to have a separate model for each aesthetic, that is also doable. So it's pretty much depends on what you want.
Mm-hmm. Mm-hmm. And another question is, do you have an intuition on how SmartGD can achieve lower stress than other stress minimization methods like Neato?
Good question. So our observation is that since we can actually continuously improve the layout example we have here. So basically, for each time, we just compute the stress value during the training of the current real layout and also the fake layout we just generated in the current epoch. So whenever the fake layout outperforms the real layout according to the stress value, then we just replace it. And you can see that we actually continuously learn from a better and better real layout, then we have a better chance to be to achieve the optimal layout with respect to the stress. I think that is the essential reason why we can outperform some stress majorization method also.
Thank you. Very interesting. We have to move on to the next talk, so thank you again. And we will hear now AdaMotif, graph simplification via adaptive motif design. And it's presented by Zhou from Shenzhen.
Hello everyone, I'm Zhou from Shenzhen University, China. Today, I will introduce our work titled AdaMotif. Here is the outline of my talk. Now let's take a look at the introduction. Our paper addresses an important and challenging problem, how to analyze logic graphs. In the field of graph visualization, graph simplification is one feasible solution for logic graphs. Currently, research on simplifying logic graphs mainly focuses on two directions: glyph-based simplification and graph sampling. Glyph-based simplification abstracts the graph structure, while graph sampling reduces the number of nodes to achieve simplification. However, these methods cannot emphasize the community structures in the graph. In the field of graph mining, community structures can be analyzed through graph clustering, graph alignment, and graph summarization method. However, the results of this method are often not intuitive. Therefore, inspired by the motif simplification method, we propose an adaptive motif method that integrates graph visualization with related graph mining techniques to reduce visual complexity and is well suited for analyzing community topology in logic graphs. This is our representative figure. On the left, the original graph shows that only communities with a large star-shaped structure can be clearly observed, one of which is highlighted with a gray box here. Communities with other structures are difficult to identify due to the high density of nodes and edges. On the right, our result displays communities with both large star-shaped structures and other structures that can be easily identified. The two highlighted communities represent the same one. To facilitate comparison, we align them vertically. We can observe that our motif effectively captures the star-shaped structure of this community. Many structures that are not distinguishable in the original graph can be clearly identified in our result. For example, the two highlighted communities are the same one. We have aligned them horizontally for comparison. You can see that the nodes of this community are highlighted in red in the original graph, and it is evident that these nodes are relatively scattered, making this community difficult to identify. However, our motif for this community effectively captures its structure. Overall, our results provide a clear representation of all the community information. Now, let's look at our detailed design. Our framework consists of 4 major steps. This figure illustrates the framework of our approach. The original 4-step layout is shown in Figure A. In the subgraph partition step, The graph is divided into 9 subgraphs, each annotated with a different color in B. In the hierarchical clustering step, these 9 subgraphs are clustered into 3 categories indicated by gray dashed boxes here, with each category selected alongside with a representative subgraph highlighted with a red dashed box. These 3 representative subgraphs are then clustered into 2 categories, as indicated by gray dashed box here. In the subgraph layout step, for the representative subgraph category with 2 graphs, a supergraph is synthesized to virtually represent their similarities in the layout, as shown here. After fixing the layout for all representative subgraphs, in the adaptive motif generation step, each non-representative subgraph in figure C is compared with its representative subgraph to generate its layout. Similar nodes are retained, while different nodes are marked in white or gray with an outer ring. 9 motifs for each subgraph in figure C are generated and illustrated in figure E. Finally, the sizes of the motifs are scaled according to the number of nodes in the respective subgraphs, and the final result shown in figure F is generated by performing an overall layout. Next, we will describe each step in detail. In the subgraph partition step, we focus on community information. We use a major community detection algorithm. Here, we can see that most communities are easily identifiable with color. However, at the center, the communities in yellow, orange, and cyan are intertwined, making visual analysis challenging and highlighting the need for graph mining algorithms. In the hierarchical clustering step, the 9 subgraphs are clustered into 3 categories. Then, for each subgraph category, we compute representative subgraphs and conduct another round of clustering on these representative subgraphs. Here are the 3 representative subgraphs, which are clustered into 2 categories. The subgraph layout step has 2 components: a similarity-aware representative subgraph, which is designed to illustrate the similarities between representative subgraphs, and a different-aware individual subgraph layout, which is designed to illustrate the difference between subgraphs in the same cluster. In the adaptive motif generation step, our motifs are generated based on the subgraph layout. The size of each motif indicates the number of nodes within the corresponding subgraph, and the colored outer contour represents different subgraph clusters. We can see that these 4 blue labeled motifs belong to the same cluster, but their different sizes as well as the white and gray nodes with outer rings highlight their difference. For the edge connecting each pair of motifs, we use grayscale value to represent the number of edges connecting the nodes within these motifs in the original graph. A darker grayscale value indicates a higher number of edges in the original graphs. Additionally, we apply an edge boundary technique to enhance the overall visual effect of our method. After describing our adaptive motif design, let's take a look at our experimental results. This is our case study on the CPAN dataset, a collaboration network with about 800 nodes and 2,000 edges. A is the original graph, B is our result, and C, E, G are 3 communities highlighted in the original graph using colors. D, F, H show these 3 communities in our result. For easy comparison, we align the same communities side by side and use the same color. Through comparison, it can be observed that our motifs effectively represent the communities scattered in the original graph, making them clear and easy to identify. This is our case study on the AS733 dataset, an autonomous systems network with about 6,000 nodes and 13,000 edges. Due to the large scale of this dataset, we use both colors and bubble sets to highlight community information, as shown in Figure 8. Although using bubble sets can better represent communities with scattered nodes, it is still difficult to recognize any community in areas with too many overlapping communities, such as here. Therefore, it is necessary to represent the communities in a consolidated manner to avoid overlap. Our AdaMotif approach does just that. Through simplification, as shown in Figure C, the community information becomes clear and easy to interpret. To further verify the effectiveness of the method, we also compared the primitive AdaMotif result with ours. Due to time constraints, we cannot elaborate in detail, but if you are interested, please feel free to read our paper. We also conducted a formal user study. The user study compared the AdaMotif method with commonly used force direct node link diagrams. To guide the user study, we formulated 4 specific hypotheses here. Here is the detailed information about our user study. Here are the results. For further details, please refer to our paper. Finally, let's look at our conclusion. In conclusion, we propose a novel graph visualization simplification framework. Our future improvements are as follows. Thank you for listening. If you have any question, feel free to contact us.
Thank you very much. Very interesting. I take a look at the Slido. There's no question. So let me start with one question. Your motif-based simplification is, let's say, very suggestive. Like you very clearly highlight these detected subgraphs and their way of how you show them. But of course, there's a big difference to the original, maybe just stress minimization or other layout. So isn't there a danger that you interpret things in the graph that are not there because of this kind of very heavy clustering and finding these motifs?
Basically, our method is good for graph with clear communication structures. When the graph does not own any clear communities, the advantage of our approach maybe can be weakened.
Yeah,
and for extremely large graph, also our method is still limited by the computer memory and screen size. For example, for extremely large graph, our approach can still suffer from the scalability issue in terms of computation time and virtual collector. Yeah, so in the future, we will improve the scalability of our method to handle larger graphs. Or one possible solution is to use GPU accelerated algorithm to handle super large graph, or design some method for a multi-layered display to address the issue of the small screens.
Now there's a question in the Slido. Can this approach be expanded to applying overlapping community detection algorithms while subgraph detection?
No, our community not overlapped. Maybe we can put in our future work.
Yeah, okay. And then there's a specific question to your one example. How did you decide on 3 clusters? Have you considered adaptive sizes, like getting more clusters?
Which example?
I think you showed this one example where you analyze the graph, and in the clustering step, you find like 3 clusters.
We have. Do you mean the? Maybe this example, right? 3 overlap.
And then you have this box where you have the steps of your algorithm. I guess the question refers to that box.
Box? Which box?
So, like,
So
I mean, the question is there an adaptive, the clustering, is it adaptive to any kind of number of clusters?
Maybe we cannot handle too many clusters. If you have too many clusters, maybe we have too many motifs, so we still need to put it on the multi-layered display. Maybe better.
Yeah, that is clear. Yeah. Okay, so thank you.
Thank you.
We move on to the last presentation for today. HiRegX, Interactive Visual Query and Exploration of Multivariate Hierarchical Data by Hao-Tian Mi.
Okay. Hello everyone, I'm Hao-Tian at Beijing Institute of Technology. I'm honored to present our work, HiRegX, Interactive Visual Query and Exploring Multivariate Hierarchical Data. The hierarchical data is widely... okay. The hierarchical data is widely used in many application domains, like biological data, organizational structure, and repository in social media. Exploratory visual analysis are often used to analyze hierarchical data, which involves visual present, search for novel observation, and abstract insight. This process is often refined and repeated many times. Visual analysis techniques such as visual encoding and querying enhance the EVA process. Significant progress has been made in the visual encoding of hierarchical data, while the visual query remains a challenge. Specifically, in an EVA process, users often lack a clear idea of query targets and must try different queries to reach a goal. Existing techniques allow users to query multivariate hierarchical data by programming and interactive filtering, which are either limited in expressiveness or lack simplicity. So we seek an efficient and expressive query approach that user can easily understand and utilize. We hope to integrate this query capability into an EVA system, enabling users to perform data analysis in a closed-loop manner. So in this work, we present HiRegX, hierarchical data regular expression. For querying multivariate hierarchical data, we aim to ensure its expressiveness and conciseness. The grammar support various query targets like node, path, and tree. Additionally, we also allow users to specify the composition of query targets. A node is the basic unit of hierarchical data. The node expression enables users to specify patterns for node attributes. We divide the attributes into two categories, the inherent attributes and the additional attributes. Based on the node specifications, we define the path expression to signify parent-child relationships. We adopt operators from regular expressions to make the grammar easy understanding, and the HiRegX employ a lazy matching strategy. The path expressions support parent-child relationships, yet the hierarchical data also requires the determination of sibling relations. To specify the sibling relation, we introduce a branch operator, which merges multiple paths. Notably, an inner path within a branch can be followed by another. More specifically, in this example, the node in the blue indicates the matched part, while the node in the red indicates the unmatched part. Besides, we also provide the element composition to specify the composition of the query targets. To make the grammar easy to understand, below is a visual representation of the query target, which we have also integrated into our system. This is a node expression and the path expression and the branch expression. Based on the HiRegX grammar, we present a query-based exploratory framework rooted in the visual query sense-making model. The framework provides three modes for different requirements. Top-down mode is designed for a goal-oriented query process where users have a clear understanding for the target pattern. They can use the hierarchy to describe it. To reduce the user's cognitive burden, we propose a visual operator for each component in hierarchy. The bottom-up mode is a data-driven process, enabling users to identify something of interest from the data collection. In this mode, user may initially unclear about the query targets. Therefore, we provide a recommendation method based on a predetermined expression and the data collection. The context creation mode aims to assist the user in understanding the data distribution and offering relevant data as context for each query result, thereby assisting user in the subsequent exploration. We construct a semantic overview based on the topological structure of hierarchical data using a deep learning-based graph embedding method. Our goal is to learn a low-dimensional representation, ensure that the data with a similar structure are adjusted in a two-dimensional space. We have integrated the framework into a system called Tree Query ER, which includes 6 panels. The data collection overview panel is for the context creation mode, the data distribution panel, the tree visualization panel, the query result panel, and the visual edit panel for the top-down exploration mode, the expression recommendation panel to support the bottom-up data-driven inquiries. We validate the above techniques from 2 aspects. First, we utilize the hierarchy grammar to specify the tasks under the EMLTT framework. Among all the 213 tasks, hierarchies can support 174 of them. Among the tasks that are not supported, 7 of them involves no query operations, and the remaining 32 tasks necessitate user interactions, aggregation, and computation after query. Besides, we validate the utility of Tree Query ER by collaborating with 2 expert users. To assemble a thorough dataset for our study, we crawled a total of 1,644 research papers in the field of visualization. The task is to explore how research in graph visualization intersects with deep learning. The first step, they queried papers related to graph visualization through the top-down mode. Then add branch expression as constraint to query papers set by deep learning related paper, and use the bottom-up mode to modify the parameters. Then they identify the anomalies through the context creation mode and got a new expression. Then they refine the expression interactively and finally got the interested data. And here is a video to demo the above process.
Retrieve all papers related to graph visualization by filtering all papers containing graph in their keywords list. Based on the query expression, the experts obtain 194 papers. The query results are obviously too large to analyze and therefore require more constraints. They further to query the papers cited by more than 5 papers related to AI. They add a branch with more than 5 repetitions in the visual editor. The query result only consists of 1 paper because setting a paper cited by more than 5 AI-related papers is a relatively strict constraint. From the expression recommendation panel, R1 and R2 learn that the number of papers cited by 1 or 2 AI-related papers is 33 and 10, respectively. They select the cluster in the overview panel for further analysis. They found that some citation trees only consist of a few levels, which indicates that the research topics of these papers are out of date and do not attract iterative explorations by researchers. Therefore, they added a new branch to constrain that the descendants consist of more than 5 papers published after 2019 and repeat 2 times. The system returns 19 citation trees. The query results consist of several trees whose papers corresponding to node L have no subsequent citations, which means these papers do not have much impact. However, the experts want papers to be cited by AI-related papers and influential papers in AI. So they set a constraint about the citation attributive node, L, should be greater than 10 and added a new branch to limit the papers, L, cited by at least one highly cited papers. From the expression recommendation panel, they can find an expression corresponding to one query result, the most related result for the expression. After retrieving the paper, they explored the overview panel and found that many nearby trees contain one common paper and the reference tree under this paper is quite large. Therefore, R1 and R2 agree that the tree containing the above paper in its field is significant and can satisfy their intents. First,
in conclusion, in this work, we propose the hierarchies, a declarative grammar designed for query multivariate hierarchical data. Based on hierarchies, we developed a query-based exploratory framework, which consists of top-down pattern specification, bottom-up data-driven inquiry, and context creation data overview. We implemented a prototype system, tree query ER, to integrate our framework. In the future, we plan to enhance the scalability of our approach and to improve user construction efficiency. We will explore natural language processing techniques to generate corresponding query expression and description based on the large language model. That's all my presentation. Thank you.
Thank you very much for this interesting talk. I'm checking the internet. I don't see questions right there. Let me start maybe with one. So what are the limitations of this kind of grammar-based retrieval? I'm sure there are several situations where these grammars cannot describe certain research results.
Yes, there are many grammar, but our grammar is only for the multivariate hierarchical data, not for the graph, not for the table, and so our scope is very small, and so that our grammar can be very easy to understand, and our tailored situation is the exploratory visual analysis. So we should to integrate our grammar into a system, and and you can see that we design a framework, from top down, bottom up, and content creation, and integrate our grammar into it, and so that user can use the system and our grammar to really perform the data analysis. So that's why we design the grammar.
Yeah. And my second questions, I guess you already answered, because I was wondering if you could use a large language model to instead of specifying that with your interface, you could just write and say it, yeah? Give me all the papers, yeah? That you say you will do that in the future work, but how will you do that? How can you use an LLM or other mechanism to really have natural language input?
You know that the large language model is very popular right now, and I know that there are some works try to transfer the text to the SQL, and our grammar is also a query grammar. So we will try to we will explore to use the large language model, try to transfer the natural language, from user. They want to get the high cited paper directly into our expression.
Yeah. Makes a lot of sense. Yeah, very interesting.
Thank you.
Good. So I don't see any more questions. So thank you for your presentation. Thank all the speakers in this session, and especially also our technicians who did that in a very way. So everything worked very smooth. Thank you all, and see you in the next session.